Anyway, it's that talk you were waiting for. We should probably make it a quick one so Timon can get back to bed. Yeah. Get up.
All right, so I made it. Sorry about that. So I decided to one-up Walter and actually do my illustrations like online. So next to like stack lifetimes, there's a heap lifetimes, like GC heap lifetimes that basically are infinite. So I finished my slides now. All right, so what is this talk? I will talk a bit more about my ideas, how to maybe evolve the language. This is still a largely aspirational talk, like most of the times when I'm talking. You may, however, learn something about existing features and the limitations, and if you'd like to contribute to you may find some project here. Why didn't I make it in time today? So this is... I mean, you may think that the issue is that those clocks are too close to the talk, but actually, this is my own Swiss time zone. This is an hour earlier. You may think the issue was that the volume was turned off, but it turns out that no, the volume was at maximum. So it can only be that the problem was that I only set 2 clocks. So next year I will set at least 3. Okay, so if getting up on time is not it, what does qualify me to give this talk? I actually received this important award at this year's PLDI for my contributions to the Rust programming language. If you're asking yourself what my contributions to the Rust programming language were, this is it. So basically... Yes, I mean, I told them that this is my only contribution. They said it's an important typo. All right, and other than that, I'm also the lead developer of Silk, which is a quantum programming language. And in quantum programming, you actually have to care a whole lot about value lifetimes, because if your values live too long, your quantum advantage is gone. And this is just like foreshadowing of what's to come. Maybe some of the slides will not be finished, because I intended to look them over this morning. Okay, so what is this talk about? Basically, there are locations and there are values. Locations are memory locations, or stack locations, there are heap locations. Maybe they're manual C heap locations or GC heap locations, while values are an abstract concept. A value may be stored in one or more locations. Locations and values kind of have independent sorts of lifetimes. You have lifetimes on the stack. Those are nested like this. So those are the lifetimes of variables, right? Whenever you declare a variable, it will be the variable in your function that is alive the longest time. And if you call a function recursively, you will have another nested stack frame that is even smaller, right? Then there's the GC heap. As I said, it has a virtually infinite lifetime. Hopefully, not a lot of your memory actually has infinite lifetime, but the GC abstraction is designed to let you believe that all your GC values have or all your GC locations have infinite lifetime. And then there's malloc free, where you can do stuff like this. So basically, this is a non-nested lifetime. You can even access your location after it has been freed. And value lifetimes, this is what I'd like to be basically delimited between a constructor and a destructor. Ideally, you can put your values inside locations, and as long as those locations are live, you can kind of copy them around, maybe even move them, which will be another topic of this talk. What you shouldn't do is, as we've seen here, have a value whose lifetime is larger than the value of the location it's stored in. In general, value lifetimes may overlap arbitrarily, so they're a bit like the manual lifetimes. So next we talk about copies versus moves. Copies is the default behavior in a lot of languages. It was copied from C, pun not intended. Basically, by default, if you assign a value to another value, you are then able to use both of them. For moves, it's a bit different. Let's say a copy works like this, right? Where you create a new value, and then sometimes later you destroy both of them. For moves, you actually just get rid of the old value, and you only keep the new one. And then, of course, after that, you're not supposed to still use value A. So this is A and this is B. Right? Actually, right now, what this move here will do, so this is a focus function, and it is implemented within the language, or a core function, actually. It does the move, but then it also reinitializes this variable with the init value. So you're actually kind of allowed to access it, but maybe you don't want to. Let's talk about constructors and destructors. Of course, how they work is you construct a value, then it is live for a while, and then you destruct the value. This seems kind of basic. Importantly, as far as I'm aware, nowadays stack variables are always destroyed if they are constructed. However, the previous slide was still aspirational. Actually, stack variables can be accessed before being constructed, and it seems I didn't insert the example here. What this was supposed to be about was that you can have some struct with an immutable field. And then you have a constructor, and you have some method foo that actually accesses the pointer p. And in the constructor, you first call foo, and then you initialize p. Yeah. This works now, and this actually violates immutable because you access a memory location before it has been initialized. And for immutable data, that's actually kind of significant because then you can create pointers that are immutable, yet their value changes. It's a bit similar for destructors. So there's this pun function here. So what this does is it creates a locally nested struct S. This struct S in its destructor escapes the pointer p, and then it has an immutable constructor that takes an immutable pointer, assigns its own pointer. And of course, what will happen here is if we construct an immutable S, then the unqualified destructor will be called on the value. We escape the pointer as a mutable pointer, and so we can actually type pun in safe codes an immutable pointer to a mutable one. The part below is also interesting, but it's unfortunately not showing. What we have here first is we create some immutable pointer, right? Then we type pun it to a mutable pointer. It's typed as an immutable pointer. If we write it, it says 2. Then we assign to the puns variant, we assign 3. And then we print the new value of x. So it's actually a good thing that this is not on here. So I can ask you, who thinks the value that will be printed for x is 2? Who thinks it is 3? That's more people. So actually, what is printed is indeed 2, because DMD knows that this is an immutable value, and of course, they're not changing. But you're able to hint it. So if you see here, I've added an assertion that obviously says that p is x. So if you add this assertion, which will pass, then the value that will be printed for x is actually 3. Yeah, so this is what's known as undefined behavior, and we don't like it. Another point is you can actually destroy stack variables without constructing them. Who wants to guess what this code will do at runtime? So we have a local struct t. In the destructor, it accesses the local variable x. Then here we have a struct s. It has a field t. It does initialize t, but unfortunately it never gets there because something else happens. Okay, so I just tell you, it will just take fault. Let's talk about safety. What does safety mean? Safety means bad things do not happen. It means you get up on time when you're supposed to give a talk. But safety is often qualified. So you say we're safe against this kind of issue. So for example, if you're memory safe, you're not necessarily safe against someone disabling your clock, but it probably helps. Memory safety means that all behavior of a function is defined. And a closely related concept is type safety, which means that well-typed programs are memory safe. Languages like D or even Rust are not type safe, so they're well-typed programs that will corrupt memory. And the common aim that both languages have is conditional type safety. So basically, if certain things are assumed about the programmers, if they do certain things nicely, then the remainder of the program will be type safe. So it's important to note that memory safety is the lowest common denominator notion of safety, so it is required for any kind of safety. Memory unsafe programs often suffer from remote code execution exploits, so you can cause any behavior you want.
Well, I disagree with your statement that memory safety means all behavior is defined. I think of memory safety as being there's no possibility of memory corruption.
Yes, but I mean, there's a difference between undefined behavior and non-deterministic behavior. So basically, what you could do is you could say, if I do not initialize this stack integer, its value will be any value in the valid range of an integer.
That's correct.
What you cannot do is say, if you access a value that was uninitialized, like an uninitialized integer, then the behavior is undefined. That will not be safe, and that is what C does. So I think C and D differ here. So actually, you can create an uninitialized stack integer in D in safe code.
Yes, you can, but you cannot use it to cause memory corruption.
Yes, exactly.
Okay.
But that does mean it has defined behavior, even though the value is unspecified.
Okay, I understand your point.
Yeah. It's a bit technical because all those terms have clearly defined meanings, and they're not that intuitive sometimes. As we saw before, dsafe has some soundness holes, and this is actually not surprising. So a good rule of thumb is if it is not formally verified, it is probably unsound. If it is formally verified, there is probably a bug in the specification, so your proof is meaningless. If there is no bug in the specification, then there's probably still some other part of your system that is not formally verified, and that is where you're attackable. If your entire system is formally verified, you can still have holes in the formal system itself. So there's still possibility for bugs there. This is one of the reasons why software licenses usually say absolutely no warranty of fitness for any particular purpose, which basically means my software is useless, do not try to use this. And the way that the programmers often cope with this is to say, well, I just don't write bugs. I mean, this doesn't affect me, therefore, right? But I would say this is, without formal methods, basically delusional for any non-trivial system. So type systems are actually a lightweight form of formal methods, and they are widely deployed. So formally verifying them in turn can be quite consequential. But in practice, they're usually holes. So other type systems are unsound too. I'm not singling out D here. Like the Rust type system is unsound right now. There are some holes in the Java type system. You can essentially pan any class type to any other class type without the cast. Of course, the way it's translated, the JVM itself will actually do a cast and catch it at runtime. But in practice, this is usually the case, unless you take efforts to formally verify stuff. So I would like to take this opportunity to address common misconceptions about trusted. So a lot of people think trusted means this function is memory unsafe, do not even attempt to check this. But this is not the case. Trusted means this is memory safe, but not checked. So this is actually one of the few keywords indeed that has a name that makes sense. And this memory safety of trusted functions is actually the precondition of this aspired conditional type safety guarantee. So basically, if all your trusted functions are memory safe, then so is everything else that type checks. The precondition is, of course, vigorously satisfied if you do not write any trusted code, or maybe nobody else writes any trusted code that you're using, which probably won't happen as you're still based on the standard C library, usually. I mean, for now, it doesn't happen. Maybe at some point we get there. So therefore, at safe is intended to yield a type-safe subset of the language. So if stuff in safe type checks, it should not corrupt memory. At life does not tie into this conditional type safety guarantee. So basically, it does not give additional safety guarantees for code that is already safe. Of course, it may still help you with improving memory safety of a specific piece of system or trusted code. It basically depends on what you're doing. You should consider it, I think, to be a linting tool that is helpful with a specific, quite restrictive way of writing code. This is not really like Rust's borrow checker, even though it technically checks borrows. And it may be a good basis for future type system extensions that do give more conditional type safety guarantees. However, I think we should also consider, is this really the only kind of linting that you want in system and trusted code? And I would imagine that it would make sense to be able to enable the standard safety checks as well in safe and in trusted and system code, and then just disable them surgically. So I think that will also help catching memory safety bugs. All right. The GC variables also have lifetimes, and they're actually kind of interesting. All right, so we have this simple program. What this does is it allocates an infinitely long singly linked list. All right, so I limited the virtual memory that this process will take up so that my machine that is running my presentation doesn't crash. Who thinks this will run out of memory? Attila is feeling courageous. Okay, so that's surprisingly few people because I can now run this. And why did it terminate? That is very confusing. I mean, this wasn't intended to be there at the start anyway. I think I just screwed up the syntax here. All right. So now it actually runs. Before it was just passed as an argument to the ulimit. Okay. So it runs out of memory. So Attila was right, and he was rewarded for his courage. Now, let's not print head. Let's print Gehr instead. So who thinks this will run out of memory? Dennis is feeling courageous. And anyone willing to join him? Nice. Yes, we have quite a few people now. So Attila was a trailblazer last time. He took a risk and succeeded, and so now there's a gold rush. All right, so let's run this. Oh, it ran out of memory. So now let's not use DMD, right? Let's use LDC. Who thinks this will run out of memory? You're very confident about LDC's capabilities. Yeah, it ran out of memory. Right. Okay. So now let's enable optimizations. So who thinks this will run out of memory? Oh, we actually have someone who thinks with optimizations it will still run out of memory. Yeah. Yeah, I mean, technically, maybe Sebastian is right. We don't know. So basically, what may happen is that at some point we allocate a piece of memory that is pointed to by some random garbage on our stack. And at that point, it will run out of memory, but it's quite unlikely to happen on 64 bits. So, yeah, who knows? Maybe someday in production, it will just blow up and run out of memory. All right, so that was my attempt to make you feel anxious about GC. So basically, if you don't run out of memory, also try it with optimizations disabled. You may then run out of memory. So basically, the issue here is that garbage collection in general is undecidable. Tracing GC is only an approximate heuristic because it says data can be deallocated when it is no longer reachable, but in practice, actually data can be deallocated when it will no longer be accessed. So this is now how it works in practice. This is not how the language needs to define it necessarily, right? But in practice, the optimizer will be able to remove some variables that are no longer accessed, like that variable elimination. And then you will actually no longer have a pointer, and the tracing GC will not find them, and then we'll be able to deallocate. So therefore, that means that compilers can and do sometimes optimize a program that has a memory leak to one that does not. And such a program might blow up sporadically in a hard-to-explain way if a false pointer appears. So like I told you. But we didn't observe it today. All right, so now let's stop the FUD and talk about the nice things about GC. In my experience, if I use the GC and if I avoid type qualifiers, then memory safety is very rarely a concern, even if I do not use @safe. And if I do not use @safe, the main potential source of unsafety is escaping stack references. And by the way, if I use @safe, still my main concern is escaping stack references. So what are the... okay, Phip?
I think also if you don't use the release flag.
Yes, that is important. I never use the release flag. It should be removed. It should be burned. It should be purged from the Git history. So what are reasons to use @safe? And actually there are two reasons that I can see, like two main reasons. And they're kind of orthogonal to each other. One of them is you want to have simple code that is obviously safe. That is quite nice because then maybe you can actually review code and the compiler may actually be able to ensure safety. And then the other reason is you may kind of need expressiveness. So maybe you're trying to do something that is really error prone and you want some assurance that it works. So even if you're drunk and or tired, and you do not really want to worry about having a week-long debugging frenzy right in front of the release deadline, because apparently sometimes in a hard-to-explain way, your program corrupts memory. What I think about this is basically that one of those is more interesting. Of course, I'm all about expressive languages, but the other one is both easier and more important for getting taken seriously in practice. Because if you do not get the basics right, then people may think you're not memory safe, even though you're essentially as memory safe as any language that exists. But not exactly any, but like any sufficiently popular one, let's say. This is about the simple safety. So are we type safe yet? And the answer is no. We need initialization safety, especially for immutable values. It would also be useful for non-null pointers if you ever add that. It would be good to have fully reliable stack reference detections. Like at the moment, if you slice a static array, that will kind of not be detected if you don't use DIP 1000. And if you use DIP 1000, you can, because it has some unsoundness as well, you can even get into situations where escaping an array literal gives you memory corruption. So it is not a strict improvement at this point in time. Maybe it even makes sense to promote all stack reference to the heap, not only those existing closures. This is what some languages do, but I don't know. One thing that I think is here important is a GC that works better both inside and outside of single-threaded batch programs. So I think the GC currently works less well than it could in single-threaded programs because it still takes a global lock. And in multi-threaded programs, it doesn't work because like contention on the GC lock will just turn your multi-threaded program into a single-threaded one, and you will still have the lock overhead. So I think it's really important to have a GC that doesn't suffer from this, and therefore I would like to thank Steven and Amori for all their work in this direction. It would be good to find some way to deal with in-out. I mean, maybe take it into a shed, shoot it. I mean, that's just one way to deal with in-out. We should fix type checking for qualified delegate contexts. At the moment, I think that just has never been implemented, and it's kind of random how it behaves. We should fix closure allocation in loops. So at the moment, if you allocate the closure in a loop that accesses loop local variables, then you actually have a lifetime unsoundness, because it will not allocate one closure per loop iteration, it will allocate a single closure. So one way to deal with this is to disallow this pattern. Another way to deal with this is to actually allocate the closures properly. Then finally, I think it would be good to think about ways to validate DMD against the formally verified implementation of the fully lowered D subset. So for example, we could create a small subset of D that has everything that is not related to metaprogramming, and this is actually not that big. And then maybe we can verify the safety checks on that thing. And then we can generate programs and check that DMD indeed rejects the same set of programs. And we should also fix all the other bugs that do not fit on this slide now. In terms of expressiveness, are we expressive yet? And I think not really. I mean, DIP 1000 has some significant limitations while also being quite confusing, maybe at first. I think it is not extremely complicated if you spend a couple of days with it, but probably you can find a better trade-off. So things I think we should explore is move semantics. So this is in DIP 140 and also move constructors. Maybe we should have some, I actually forgot what escape checking for non-nested lifetimes was supposed to refer to, but we definitely need this. Yeah, right. Yeah, at the moment, the DIP 1000 will only work on stack variables that are basically, it will work on other variables if you just pretend that they're on the stack, even though they aren't. This is what Dennis did on Tuesday. Or yesterday, I don't remember. I didn't sleep enough. All right. So DIP 1000 works in this nested fashion, but I mean, in practice, you may have lifetimes like this, especially if you have memory management. But nothing stops you from doing this, and DIP 1000 doesn't really help you all that much in this setting. Then multiple interactions would be nice, because right now DIP 1000 basically tells you you're either taking the address of a reference or you're escaping the thing the reference points to, and that's it. Would be good to be able to have interactions beyond that, so that you can implement the tree structures in some sort of safe manner, even though you may be using a linear allocator for all the nodes, and you want to use actual pointers. Another thing that I think is quite kind of crucial is that the DSN effect system, it doesn't have effect polymorphism, and this is why Dennis had to break the type system. So actually, his GC allocator was no GC. I mean, I can't see what's wrong with that, but maybe you can figure it out. So effect polymorphism, what this is basically you have to be able to say this function is no GC if and only if the callback that I'm passing to this function is no GC, or some other thing is no GC. At the moment, I mean, we can kind of do this if we pass the callback as a template, but as I've heard, we're trying to reduce template usage, and I think to reduce template usage, we should really try to explore this sort of parametric polymorphic type system extensions. But I think we should only start doing this once we've verified what exists. We should have attribute inference for recursive functions. This is kind of hard to do efficiently. I have some ideas about how to do in a way that doesn't have efficiency guarantees. Maybe just conditional attributes would be nice, so that you can specify yourself, well, this thing is safe if and only if this part of the input is safe. Then you can work around cases where inference just fails. And it would also be good to have better escape analysis in the front end. So maybe I've prepared another. Yeah, right. So who thinks that this allocates with the GC? Maybe I should show you the compiler options. I don't know how this works. Okay. So this is it. I was supposed to have this as well. Now you can probably see most of the function, and you see, well, no, it doesn't GC allocate. Who thinks I can make this function no GC? Like just the function foo. Can I make it no GC?
It's not called. Ultimately, it should be removed.
Yeah. But I mean, so you say, yeah, can make it this no GC?
It has to, I'm saying it probably can't.
Okay, so actually Mattis was right. I think he was the only one again. I can make this no GC. And that will work. All right, so now let's do an equivalence transformation. Int y equals 2. And now instead of 2, we put y here. Who thinks I can make this no GC? No one. Okay, you're right. Okay. I cannot do this, right? It fails compilation. So who thinks this function allocates with the GC? Yeah, I mean, it doesn't. I mean, as you can see here.
It allocates the closure.
Yeah, it doesn't, because this is LDC and I've passed the O3 flag. Of course, if I remove the O3 flag, then the story is a bit different. alloc, yeah, alloc memory. Here is your closure allocation. But LDC will actually often optimize it out. So just because you cannot make something no GC, it doesn't mean it will use the GC. And therefore, that's what I'm talking about when I say it would be good to have better escape analysis in the front end. It should be possible to use STD range without incurring GC overhead for simple things, even though you're not escaping anything. And I think it would be really good to have no GC exceptions, because in many cases, the only reason why focus function is not no GC is because it may throw an exception if you call it with arguments that you shouldn't have. I mean, there is DIP 1008 here, which basically it's a reference counting scheme on top of throwable. I don't know if this is the right approach. Amori had some ideas, I think, where it just says, well, when are you ever going to actually leak an exception? So just delay the GC allocation to the call site and attribute it to the call site. So I think that would also make a lot of sense. And then finally, it would be good to have some way to express ownership, or that some graph of pointers is isolated. Okay, I mean, we have what we have, and it's actually already quite expressive. I do not want to discourage you from experimenting with what we have. One indirection is kind of enough for anyone, as Robert showed with his tuple of arrays approach. We have system fields. We can actually implement non-trivial type system features in the library. Not anything that requires polymorphism or dependent typing. It would be nice to have something like that. Then system fields would become even more useful. You can use fake stack references, like Dennis's arena design, where you just act as if your dynamically allocated pages lived on the stack, and that gets you somewhere. And then you can also do runtime checks instead of, or to complement type system features, because range checks are how we took care of buffer overruns. So we have like range checks on array accesses, right? We can also do this for use after free. There is like not much stopping us, except that, of course, for this sort of temporal property, you will need to instrument your program with additional data. So it is a bit more expensive in terms of data, and data is more expensive than compute, so the trade-offs are a bit different. But you can still make your program have a more predictable running time. With DIP 1000, we can actually use Go pure static callbacks, and kind of have this sort of continuation passing style that, again, only works with nested things. But this way you can actually prevent things from escaping. This is an example of what you could do. We could have borrows that are checked at runtime with this syntax. It's not the nicest one. And I was tired last night and forgot that return is actually a keyword. Yeah, so we can borrow, and then what do we do after that? We cannot return. That will be tricky. But I mean, you can't just do this, right? You can do this today in the existing language. This works. You can just add some flags to the vector, or maybe just some count of how many things have borrowed out. The details are, of course, maybe a bit tricky, but we can do this today, and this will be safe. So now I have like 4 minutes to talk about DIP 1040. So basically, it proposes to move the last use of a variable. So basically, we can move the last use of a variable, and that is fine. So I've disabled the copy constructor here. So if you actually have something that is not the last use, it will call the copy constructor. In this case, it will error out. And I think DIP 1040 is a big step up in the usability of move-only types.
Doing the move in the last use of the variable, that will also make the destructor run earlier. That could have like semantic side effects.
Yes, so it has effects on lifetimes, which means it is unclear how it will interact with DIP 1000. But I guess what it will do in practice is it will just leave behind the old memory location in the init state. And then if things access that, then it's maybe not memory unsafe, but it's still not nice. So it would be nice to be able to check this. But yes, that's what DIP 1040 does, right? I do have some criticism of DIP 1040 as well. So move-only types can support like value tab, like referential transparency, which means they're efficient mutable updates and no implicit costly duplication. So I think this is quite a nice trade-off. You don't even have to think about how to copy your data without causing aliasing that will trip you up later. And they can behave like resources. So you can actually count, I've given out this many of this value, I've received this many. And D essentially supports some substructural typing via disable of special member functions, or even just via a system private on those special member functions. So in principle, maybe it will be possible to statically ensure that you return, I don't know how to call it, all your borrows, right? Maybe you return to the wrong vector without dependent types. You cannot check that, but you can at least check that it didn't forget to return stuff. And then it would crash at runtime if you're passing it to the wrong vector. So structs in D are always implicitly movable, and without the move constructor, this means structs cannot have internal references. This means C++ interoperability gets tricky because I think STD string usually has internal references. So it's good to have move constructors, which is proposed by DIP 1040. What is a bit dangerous about DIP 1040 is that the move constructor implicitly passes by ref, which means it just will not destroy the argument, and the caller will move it, so it will also not destroy the argument. So in this case here, T is not shown, but the T is basically also a wrapper around a malloc pointer. And it has a copy constructor that just copies the data. Here, if we run this move constructor, we will correctly move X, but we will copy T. And now actually, if we run this code, what will happen is a memory leak, because T will never be destroyed. I mean, other will never be destroyed, other.t, right? I think destructor elision is very dangerous. In particular, consider this code. For this constructor, the destructor of arg will be called if and only if S and T are different types. I think we should adapt this, because this might implicitly break resource acquisition initialization. It will cause memory leaks. I think a better approach is to be explicit about destructor elision, and it should only be possible to elide destructors from the module that is defining the type whose destructor is elided. Destructor elision is also useful for unpacking, because you may want to unpack a bigger struct into its components. So there are some things that are not addressed by DIP 1040, and yeah, that's it. You can ask questions. I will show this. You can ask questions about this.
I want to refer back to the beginning of your presentation where you talked about the desire to have programs that don't have bugs in them. I found this to be a common idea among people new to programming, that they can write perfect programs. And the problem is you cannot write perfect programs. They always have bugs in them. And like when I was at Boeing designing airplanes, you cannot design perfect parts either. So what do? What you do is you plan for failure. Okay, you never bet your life on a single component or system being perfect. You always have a backup plan in case it fails. And the same goes with software. If you are writing software for something critical and you've decided that your program cannot fail, then you failed as a software engineer. You always must have a backup plan for when your software fails, because as Timon correctly pointed out, every step in the system has potential for failure.
Yeah, so I guess that means we will need a second D frontend.
Well,
I mean, I did
I
try
wouldn't
to start
object to
this,
it.
but the existing frontend stopped compiling my frontend at some point because of the issues that I was trying to address in my frontend. So maybe we can work on that sometime.
Well, it'd be a pleasure. I might ask you, all of these complaints you found out about D, I have not heard of them before. Well, some of them I haven't. You've told me about others. But a list of these in Bugzilla would be really, really appreciated.
Yeah, I mean, I think they're mostly in Bugzilla. Maybe some of them are not. But I think really a better approach here is to systematically just ensure that what you have is solid, instead of trying to fix holes in an infinite cheese grater.
Well, all I can do is fix problems.
Yeah, exactly. So that's why I think we should adapt the approach to type system soundness, so that we can actually say we validated this using a formal system.
I would like that, and I have no idea how to do that.
Yeah, I do. I don't know if I will have time to do this, but maybe that's an idea for next year's DConf.
Okay, well, I really value your help with this because that's I have no expertise in type system proofs of any sort. I just have an intuitive grasp of it. That's it.
This topic of garbage collection and whether things are safe in the event of a throw, when you were talking about that, it made me think a little bit about when you start your program and you have like void main or int main, and then you have like arguments that are on the stack, like the command line arguments. In theory, like if throw new were a special keyword that like specifically allocated to something on the stack, kind of like args is an argument to the main function, or if it was a hidden global variable that it assigned to, could that make it possible to have exceptions without having to allocate and avoid a lot of trouble?
I mean, in principle, yes, it's a bit tricky to allocate on the stack if you're going to throw, because the stack could be immediately unbound, so you would have to have some other place to put it. And then also in D, you can actually have an infinite chain of exceptions. So in general, you do need to allocate dynamically. It's a tricky question, but I think what can be done is like have some static buffer that you're using for exceptions before you do dynamic allocation. And you can use other allocation approaches before you resort to GC, and you only resort to GC when you catch an exception and then leak it somewhere else. So another issue for non-GC exceptions, by the way, is that the message of the exception isn't throwable. It is a string, and usually people just, they construct a string, and that uses the GC. That's another thing to consider.
And that's that. Thank you, Timon.
All right, thank you.